哎，没看到。
我还没刷，我这还没刷出来。
哦，不好意思，重新来一遍。我开始直播了。
我用手机刷一下，70%的电应该够。手机刷一下。哦，来了，现在进广告了。
进广告了。OK，感谢张强哥的7.9块9毛，请我喝咖啡。
能听到我的声音吗？
能听到，听见。
直播里面，
大家应该能听见我和小马的声音吧？
我这个大小还可以，但为什么我在那个位置？我操！
我调不出来，等会我再试试啊。
不，你就那样就行，我觉得挺。
没有，我这
你
因为你的是 Zoom 的，我的是自己摄像头的。
啊，哦哦，
你是时区的原因，不是9点。你是在哪里9点？在东岸9点可能。
9点应该是最东边美国哈。
对，
直播里面能听到我声音说话吗？
能。
哦，
还有4分钟，大家好。我们现在有多少人？140个人，哇，可以啊。
哦，是这样的，去。
等一下啊，我再帮你调一调，你这个太小了。
不，就那么大可以了。其实，你把我放不，你把我放在你上面就可以。你把我拖到你的，就是我觉得可以了。
你看它 default 就这么大，
啊，那就 default，
你放
要不然
在左边啊，
我就全
这样我也能看见你。
放到左下角嘛，左下角。
这儿，这吧。
对，
哪个公众号啊？可能是时区的原因吧。
你问一下那个评论区能不能听到我的声音？
能，大家
能
都
听到我声，
能听见，能听
能
见。
能听到我声音输一，听不到输二，哦，听不到也没办法说。
还有3分钟，你对这次 AI Day 有没有什么想法？
我现在我的想法是我先看一下大家能不能听到我的声音。我这还没刷出来哦，你能听到吗？
可以，可以，能。
哦，我看到刷出来了。
嗯，
哦那可以哈，那你真的是电脑方面的天才，我觉得。
搞了一下午，
哦，
别说了，丢人。
那太好了，那太好了。
我想想，这个时间在西部都是5点钟，大家刚下班，然后在东部的朋友现在已经8点了，快。
嗯，那挺好的，
大家今天晚
能有
上或者是白天本来都有什么安排吗？我看有人说要上班，有人说要，反正各种事情啊，可以分享一下。我今天晚上本来有一个游艇可以上去玩的，然后我给记错时间了，然后我就给取消了。对，
我本来考虑你说到游艇，我考虑之前我说如果赚钱赚的比较多了，就买一个游艇。结果我去坐了一次游艇，发现我自己晕船，你知道吗？
那说明那个游
然后
艇不够大，你知道吧？
那也有可能，反正我就挺担心的。本来我听说游艇还挺贵的，但现在担心以后挣了钱，那个钱该怎么花？要是不买游艇的话。
哦，日本早上9点可以的。上班的好好上班，可以放在旁边听听声音，然后回去我们做个总结。我也得记点笔记，等会儿，别到时候听不懂。
可以，这一次 AI Day 其实可能比较 technical，不知道能不能完全听懂啊？
我觉得能听懂30%我就满足了，我要求并不高。
嗯，到时候到时候那个嘛，到时候开始了以后， 要不我就把我这边静音了。
哦，可以，你自己关麦吧，我就不给你关了。
对对对，我就关麦，然后我就那个听完了，我们再讨论，你觉得怎么样？
可以，留着买特斯拉电游艇可以的。
我觉得有机会。
哎呀，
今天不知道马斯克会不会迟到
快感谢这个张的，给你也来一杯咖啡。
啊？把咖啡打到 Allen 的账上，到时候，
你
我我
来芝加哥，我带
预计，
你喝。
对，我预计最早可能我10月份能去吧，最
十月份
早的话
可以啊，
啊
10月份。其实你11月份以后，我还能稍微不忙一点，无所谓。你
啊
要来肯定也有时间。
啊，我不知道能不能参加那个股东大会10月7号我看好像是，
哎，开始了，
是吧？
大家能听见直播的声音吧？特斯拉的这个音乐大家能听见吧？听见给我一个一的回应，我确保设备没有问题啊，不要再次翻车。好，谢谢吴小娇。看看马斯克现在的飞机在哪儿？
哦，已经这么多人，
300多了。
可以啊。我得戴一个耳机。
欢迎大家一起来见证这个历史性的时刻。
Those girls can really elbow.
尴尬。我在旁边刷个推特，大家看看。Allen 18岁零2天2-3天吧，就刚刚初入社会，还请大家多多指教。对，我也很喜欢我这件衣服。SpaceX， 哦 ，Space Shuttle。小马，你说说你当时看到这张宣传海报的时候，第一反应是什么？你觉得他想透露什么信息？
我觉得可能，我觉得它硬件要改，但是我对硬件又不是特别了解，所以不敢猜测太多。我对那个就是它那个叫什么神经网络学习，我还比较感兴趣。然后听说过它的特斯拉的这个叫自动标记嘛，我觉得这个确实从我的角度来讲，能够大大提升那个它的就是效率。因为如果是人工标记，像我之前频道里的视频，我拿那个 Model Y 测试，不是撞了那个石头上面了吗？这个就是它就是没有在它的图库里面，或者说在它机器学习网络里面，它没有就是那种停车场里面摆那种大石，所以它就直接撞上去了。 那么如果在以后它的这个自动标记能够越来越有效的话，我就相信它能够更快的就是那个叫什么样的，就是解决这种 corner cases。那如果能够更快速的解决 corner cases， 我们都知道自动驾驶的这种边际的这种case， 它是就是自动驾驶最难实现的一步。如果能够越快速的解决，我相信特斯拉离自动驾驶就会越来越近。所以我在就是它机器学习这方面，我是非常期待的。
可以的。
这个 AI Day 也是相当于我们学习的一个这个窗口，可以这么说。
这个网站就是英文直播，没有中文直播。我们是试图将它翻译成中文，看这个能力吧，因为很多专业术语自己都不是专业人士。对。但北美财务自由需要挣多少钱？这个小马你怎么看？
我觉得财务自由这个问题非常非常的有意思，因为我以前看过一个非常有意思的报道，就是你问美国不同阶层的人什么是财务自由，那么比如说有50万的人，他就会说，哎，有100万的人是财务自由，那么有100万的人会说200万的人是财务自由，200万说500万，就是他不断的这样递接上去，你知道吧？就钱，我觉得是你在任何时候你都会觉得不够用的，所以在这种情况下，我觉得讨论是否财务自由，我觉得没什么太大意思。就这是一个比较无解的话题，相
对概念都是一个。
对，但我觉得相对就是怎么来评判一个人的好坏，我觉得就是一个人能给这个社会创造多少的价值，也许金钱是一个非常重要的评判的标准，但是我们也不能仅仅限于金钱，对吧？
对对对。上班吧，该上班上班，不要耽误本职工作啊。
你的这个直播是在特斯拉的这个就是它官方的那个 YouTube 上面？
对，特斯拉官方。
但是我在这刷着呢，刷到它直播。哦，在这里看到。
销售发的这个就是我视频里讲的那个高盛预计的那些顺序都差不多。
Alan 一会儿开始了，你跟我说一下，我再把那个我这边的打开，我再看。因为现在我看还在放音乐，手机没电了，我一会儿再开始放。
好的。
再唠会儿。马斯克这个一般是平均迟到30分钟左右，我觉得等时间长了，我们可以把马斯克就是这种大大小小的事件啊，当然财报他一般不会迟到，因为那个是规定好，就是这种大大小小事件，我们可以做一个这个数据统计，看一下平均马斯克要迟到多少分钟。我的感觉应该是半个小时，你猜多少分钟？
我觉得20分钟吧，顶多了。这个好可爱啊！你们不觉得这次的音乐特别的带劲吗？就是有那种在图书馆里刷题写作业那种就是工程师的感觉吗？
其实我觉得工程师应该比较喜欢那种，我不知道你啊，我比较喜欢那种比较安静的那种然后写代码，就比较 smooth， 比较那种，这种感觉怎么说呢？也还行吧。可能马斯克喜欢这种音乐啊，不知道马斯克写代码的时候是不是用这个音乐？
世界上每卖出一辆特斯拉就会少一只猫。可以的。
看一下今天能不能突破1000个人来了。
不一定，这个没有那种 Plaid S 发布会那种，就是受众广，这个就工程师或者是除非这种特别炙热的粉丝才会看。哦 ，Vincent 也来了，我靠，可以。哟，马斯克哦不对，小马学数学，计算机数学，
计算科学，computational science。啊，我本科学的数学和统计。
可以的，很 technical。
Alan 学的会计是吧？
我还学一个 analytics。
哦。
200万可以取出8个消费人8人数，那么就财富自由了。对，刚才那个财富自由的话题，可以的。
我觉得如果是年轻人的话，应该多想想如何在退休之前给社会创造更多的价值，对吧？而不要想太多什么财务自由。我觉得与其去想挣多少钱退休，我觉得不如从第一性原理去想一下，对吧？自己的价值有多少？我觉得这个反而能让你更早退休。
这个频道有准备好简历的吗？昨天我看着有人说有准备好简历了，但是发现自己不是学 AI 的，巨搞笑。感谢0easy 的谢谢你的 sticker 1.99块，谢谢，我也谢谢你。对呀，好多人做 live， 都很期待看这个东西嘛，但是感觉大部分人应该都看不懂吧。
希望我们的 live 能够怎么说呢？有所突破1000人，已经500了。
就是大家看一看无聊就退了，都这样的，很正常。必须要 trench。对，马斯克的女朋友是挺喜欢这种电音啊、2次元什么的，我觉得有可能是他选的曲，挺带劲的这个小 beat。
Alan， 之前是你发的那个投票吗？就是和波士顿机器人合作。
不是我，不是我。
哦，那反正我在哪个地方看到一个投票，就是说的。
我也看到那个了。
就是特斯拉。
我觉得有点早吧，就是现在的 focus。我看我的推特全是 AI Day， 一刷全都是 AI Day。感谢 Vincent 的9.99块，这是一个什么图片，这么可爱？粉帽子 ，Thanks bro。哇，特斯拉多头又来了，这个熟悉的名字还有头像，可以的。我直播有事件在直播呀，平时直播对吧？没有什么事情，天天跟大家盯盘嘛，那也没意思呀。哇，感谢 Vincent 啊，来支持我们啊！Boston Dynamic，
我特别喜欢这家公司。我 我之前第一次知道它的时候，我还专门去查了一下它是不是上市公司，所以我很可惜的发现它不是。
它如果说，我觉得它跟 AI 的联系就是，它是如果是 program 好去做这些东西的话，是一个阶段。要如果说它是具备自己的，比如说仿生的眼睛，或者是就是听觉，然后再去做这个场景内的，比如说这个动作的话，那就是一个完全不一样的 story 了，就屌很多，对吧？
啊，我感觉这个公司反正就我看哈，但是我不是特别了解，就是它好像就是主要人操控嘛，但是它这个我觉得比较重要的是它能保持各种机器的平衡，
对，
这个挺困难的。然后做一些那种动作，然后我觉得如果能跟特斯拉的这个视觉识别能够有所结合的话，我觉得应该很厉害。
对啊，这个就是我是说，它现在已经有这个技术让这些东西动起来，对吧？但是你看这些跳舞什么的，它都是 program 好的提前，
对，
对吧？它如果是，然后特斯拉的 AI 如果跟它可以结合起来，那个就牛逼了。
而且它这些机器人可能现在生产的价格可能也不会特别低嘛，如果就是能够大量生产的话，估计还是能够就是在科技方面有所突破。
对，这玩意儿比如说真的很酷，可以干很多事情啊，比如说去给你买个外卖什么的。感谢 Sam 杨的10块这个 Australia B 啊 No.1 fan， 谢谢，好多澳洲的朋友好像。
澳洲的华人挺多的啊。
我看早上这澳洲、日本，然后还有一些欧洲的有几个朋友，我刚才看到，然后台湾很多。
我终于和 Alan 没有时差了，之前都有时差。
我们现在不是还有1个小时吗？哎，你是在更往东是吧？
更往西，在多伦多的西边。
多伦多的西面 ，OK。
对，在安大略湖的最西边那个角。
不是，可是你是8点啊，你在西，你应该是6点。
没有，我在多伦多的西边，在芝加哥的东边。
OK。SageMaker 的东西不知道啊，我就觉得老马之前说那个 Machine Learning as a Service 那就好牛逼啊。Boston Dynamics 好像使用的是 Machine Learning 方法做 Motion Planning 和 Optimization， 可以的，大家都很专业啊。这就是直播的时候互相学习啊，非常感谢大家。汽车公司买了人形机器人全套的，成本太高，造起修不起，商用1257。OK， 感谢特斯拉多头的4块4毛9，这个是欧元还是法郎还是什么？这什么标志啊？我对货币不是很懂。
好像是欧元。
欧元是吗？Keep it up， 谢谢。怎么还没开始啊？因为老马估计飞机又延误了吧？没有办法，他实在是太忙了，我觉得。主要是最近 SpaceX 的进展也挺高的。
对，
挺快的，就是各种突破啊，又是挺厉害的。哦，这是英镑，对，英镑对。谢谢。
英镑值钱还是欧元值钱？
英镑值钱吧？我不知道，英国脱欧了之后我忘了，我就没关注过。老马没有准时过。哎，其实也正常啊，那个event正常event7点开始，对吧？肯定有迟到的人，在现场大家都慢慢悠悠的进场，然后人坐下来，老马再迟到一会儿，对吧？
有一句话说得好，就是老马 经常迟到，但从不缺席，你知道吗？这句话特别好用。
可以。
说到的一般都做到了，但只是时间上有点那个不一样，所以有些人讨厌马斯克，主要是因为这个原因。
所以他们说老马撒谎，我就觉得迟到或者是，哎，你要是严格意义说撒谎，那也没有办法。还有没有好看的视频？我觉得这个机器人跑起来还挺带劲的。
对啊，我看网络上不知道是一个 P 出来的还是一个什么，就是一个人把枪扔给那个波士顿动力的机器人，然后那机器人就把人给杀了，反正就是。
哦，我也看过那个。
就说什么人工智能要占领世界，所以马斯克估计也担心这个。
嗯。哦，还有好多马来西亚的粉丝。Malaysia 可以。感谢张方的4.9块，谢谢。对啊，你看大家都问你准不准备在加拿大再买一个特斯拉，我之前还说你赶紧买一个，对吧？
我准备等那个，现在我是这么打算的，我准备等那个 Cybertruck， 我直接提车就挺好。
你之前的 order 可以直接提吗？还是？
我好像是可以直接改到加拿大，因为我把我的那个地址改了，然后他直接就给我分到加拿大这边的上面，而且我的订单应该是比较早的，但我估计，即使现在等的话，也可能要2年左右吧。
好久啊！感谢 Alyssa in Wonderland 的这个 Super Check， 非常感谢，长期支持我们啊，经常看到。对，这位是小马，Fabio 马，我们经常聊天呢。对 ，Model Y 确实等的时间最近有点久。
是啊，国内的这个 Model Y 好像等待时间不是很长，不知道现在怎么样啊？
就上海的还等的时间应该是最短的了。美国这边我朋友，哎，我下周可能陪我一个朋友去提一辆 Model Y， 到时候拍点视频给大家看，看看现在的做工怎么样。
我觉得你拍 Vlog 其实我更倾向于看你的 Vlog。
真的假的？
真的。
我感觉 Vlog 大家还是更多关注财经之类的，拍 Vlog 感觉没什么意思。
我觉得特斯拉使用的那种视频，可能就是大家也挺爱看的。
对，哦，谢谢文森，你去忙，对吧？我们有什么在线下聊。哦，对呀，今年拿不到车就抵不了税，确实。但是我看最早一批 Model X 9月份就能交付了，我看到有人更新他最新的 sales 跟他的这个订单 Model S Plaid， 我还是挺想换那个的。如果我要换我的 Model Y 的话，我应该会换 SX。
我觉得换 Cybertruck 吧，但 Cybertruck 等的时间太长。
然后他们用途不太一样嘛，就是两个不冲突，我的意思。
你如果定 S 和 X， 你会定 Plaid 还是就是定它的长续航版？
我 Cybertruck 定的就是3电机，我 X 应该就 Long Range 就可以了。但是 Plaid 也，Plaid 这个，哎呀 ，Plaid 续航有点少。但是哎，我也不知道，主要是 Cybertruck 距离有点太远了，还不知道什么时候能出来。
我的那个那个叫什么 Cybertruck， 我还是定的双电机，没有定3电机。我消费上我还是算比较理性的，因为我觉得3电机比双电机要贵2万块钱，我就觉得有点不划算，你知道吗？
续航长啊，那个续航我要是从芝加哥开到西雅图，我充3次电就跑完了。我这次充了10几次，我靠，充吐了都。 感谢沈路的 Super Chat， 非常感谢。哦，对啊，
我觉得就是皮卡必须要是4驱的，就双电机嘛，就这么说，单电机有点那个。
但是它将来你比如说要卖到，就是跟那些汽油皮卡比的话，还是得价格还是得只有单电机才打得下来吗？
啊，是啊，它单电机我不知道，就是说它是所谓的2驱，还是就是说它把电机放在后面，但实际上是一个4驱。
没有3电，对，哦，我明白你意思，应该都会4驱吧？我猜，不知道
啊。
给大家看看我的 Cybertruck 怎么样？这是拿3D 建模打印出来的，还挺逼真的。然后后面写着字，能看清吗？看不清吗？写着 Tesla Cybertruck 2019，超酷，我觉得这个。
想一想当时那个皮卡发布的时候，那个时候才多少钱？特斯拉才300多。
2019吗？
啊。才300块钱，现在都多少了？3000多。你想一想，
真的，
时间过得真的快。当时我是真正的才刚过18岁，现在我都已经感觉自己老了好多了。
我靠！哎 ，Cybertruck 呢？几点开始 ？Good question， 理论上已经开始了，但是都在等老马。
这一次倒不一定完全是等老马，可能是等入场或者怎么样。
老马做开场白吗？
应该是，或者是，我估计老马应该要讲，不一定只是开场，也要自己讲一些他对的理念，然后比如说还有那个叫什么 AI 团队的那个人叫什么名字，那个肯定也要出来讲。
Joe Motor 300加卖，这个500加真的太吸引我了。Try Motor。
但确实，如果达到500加的续航，那确实还是基本上就没有什么。
开到累死了，还有电，就真的就是。
对，500迈确实是个坎儿。
500真的已经，500迈汽油车很多都开不到吧？
对，
英里啊，500英里，你想想，汽油车加满油都跑不了那么远。
不过现在充电也很方便，我不知道，就是美国那边充电应该是比中国要方便。反正在中国基本上就是没有任何那种里程焦虑，很多就是
对啊，中国充电太方便了。
对，就现在很多对于电车比较怀疑的，就还是我觉得，其实充电现在完全不是问题，都不只是在大城市了，在很多那种就是小一点的城市，都充电都非常方便。所以现在
中国国家电网很方便是吧？你在国内待了这半年
啊，非常方便，非常。
但它的充电速度怎么样？
充电速度反而有些时候国家电网比特斯拉超充要快，就属于这种。我估计有这么几个原因，第一个就是说特斯拉超充一般
负荷大，
就是不是它给的电压，就是不仅是特斯拉这个充电桩的问题，还有就是你在那个地点它能够给你多少电压就属于，就有些地方它就是它那个比如说充电桩它是 V3 的，它可以达到比如说很高的这个充电功率，但是那个地方的电压不支持，你也就只有按照比较低的功率充电。所以我感觉国内的就是超充和普通的那个快充，就是国家电网的充电桩，其实差距不是特别大，除非 就我有一次充那个特斯拉的 V3，是真的达到了他说的那个250左右，就只有一次，而且就只在那一个地点，然后后面其他的就基本上就是100左右，100多一点。
但是国家电网的充电，它的功率能达到吗？我也是比较好奇。
国家电差不多，国家电网的充电，就包括一些品牌，比如特来电啊这些，实际上都还可以。
OK。
都反正大部分就是40分钟，基本上就充个80%，完全没有问题。
哦，有人问我粉色水壶哪去了，换了一个这个可以带这个刻度尺的，告诉我一天可以喝多少水。为了 Cybertruck 还得换房子，对呀，一起换了吗？
为了买特斯拉买房子是吧？哎呀，
特来电是第三方里最好的。
等一下，我发一个朋友圈，说我自己在 Alan 的频道直播，我要炫耀一下。
哎呀，大家都在等啊，全网都在等啊，急死了。
等待就给了我们聊天展示。
他这个挺好玩，他说 Elon is DJing, he's not late
啊。
42分钟还是69分钟？给个水壶链接啊！我就是在 Amazon 上买的，我回去找找，可以发给有需要的朋友。国家电网安全协议太低，容易冲坏车。第三方很多品牌的确不错。
哦，我理解的那个就是除了特斯拉都是国家电网，我可能说错了，但是就是
对，
我的理解就是特斯拉超充，然后其他的都是另外一个，但是可能也有好或者不好，我是比较有偏见的。
小马和 Alan 对 Michael Burry short Tesla 怎么看？哎，我记得我们好早之前，去年第一次是不是就讲过这个事儿？他当时就在做空特斯拉，是不是？
对，首先他做空的，我不知道我说的对不对啊，就是他首先是通过期权，
对，
就是期权，反正就是你背后到底值多少钱，你从他的那个报表上也看不出来，而且他那个报告的，他就是此时此刻就那么一瞬间，他有多少的期权，也不代表他，你也不知道他持有多长时间。而且 Michael Burry， 反正怎么说呢，不太了解他这个人的战绩怎么样，但是我个人认为，我投资不管特斯拉还是以后要投资新能源计划，都是从我的角度都是说穿了，就是投资马斯克这个人，就其他的就是一些都是最主要原因还是马斯克这个人，我非常看重他这个人。
给大家看一下马斯克，不是马斯克 ，Michael Burry 做空前和做空后的图。第三方充电桩打价格战 ，OK。 哇，已经30分钟了，还没来。
快到那个就是马斯克迟到的时间了，一般是30分钟，但我估计今天会拖后一点，因为应该是邀请了不少人去，所以
我觉得这次肯定会来一些 AI 界的大佬，就是那种让人敬佩的那种，不是很出名，就是那种
业界出名，
对，业界出名，但是大家不知道是谁的那种。
对。
AI Day 会提到 Palantir 吗？应该不会吧？他们走的好方式好像不太一样。
Palantir 应该主要是大数据分析，
对，
但具体是什么业务，就也不是特别清楚。好像就是把本拉登抓到了，就 Palantir， 我记得应该是这样。
Larry Page 也在
Page， 我也看到了。Larry Page 是不是就是那个说他死了要把所有钱都捐给马斯克？是不是就是 Larry Page 说的？
很屌的他。他是97年到2001年的 CEO，Google CEO。
啊。
今天不会讲电池吧？今天主要是 AI Day 啊，讲人工智能的。所以我觉得这次定调非常有意思，就是告诉你们，我们不讲车，也不讲电池，我们就讲人工智能。你什么时候看过福特啊、通用啊，还有丰田啊什么的，什么开过什么人工智能大会，或者是开过什么科技峰会都没有听说过，对吧？但是不是去年，今年那个大众还开了一个电池日，就仿特斯拉电池日，不知道他明年会不会接着仿。
模仿是对的呀，大众至少知道了他应该跟随谁走，对吧？
嗯。
其他美国这些车企还没搞清楚竞争对手是谁，这种就很危险。
嗯。老马不要再 DJ 了，快出来吧！哎 ，Bloomberg 真的能找 Gordon Johnson 这种人来采访 AI Day， 我真是吐了。他知道什么 AI 啊？我就觉得这是在纯搞笑，你知道吗
？Gordon Johnson。
你要说他黑特斯拉 ，OK， 你要说产量交付，你叫他来，我们都能理解。妈 AI Day 你来讲什么？你去采访他，我靠！
我觉得 Gordon Johnson 他之前他可能是为那种空头工作，但我现在就感觉哈，就是因为特斯拉这个群体慢慢变大了，然后越来越多的人讨厌他了。但是你想，讨厌他就有很多人把他当作笑话，所以他这个人现在你还不要说，他自身带了非常大的流量，所以这对他来说也是一种价值。说句老实话，因为你想，这些媒体去采访他，就特斯拉的这些多头们都会去看，
对，
所以这变相就给不管是媒体还是他自己，就这是一个双赢的一个生意，你知道吗？所以 Gordon Johnson 就现在变成明星了。哎，开始了。那我就闭麦了，我就认真。
你自己闭，等我自己开啊。哦，现在自动驾驶的宣传片手要放在那儿，看到没？可以的。 特斯拉官方有33000人在线，我们直播间有700人，哇，不错呀！感谢绿树的4.9毛9 Super Chat， 感谢支持。对，手拿方向盘这样拍是对的。
Alan， 你曾经做过这个 FSD beta， 你做过这种测吗？
我还没有，但是我联系到了一个当地的有 FSD 的人，我准备过几天去找他，去体验一下，
拍摄一个视频。
对，但他也拍啊，他是一个外国人，让我看看。
没事，你就拍一个中文版。
对，我看看从我的角度拍一个什么感觉。感谢 Tesla W 2021的10元 Super Chat， 感谢支持。这个车还是这个2021款的，不知道是3还是 Y。
让我来看一下，用我的慧眼识别一下。
我感觉这个高度有点像3，但是又有点像 Y， 实在是看不出来。
看不出来。从外面看我看得出来，就是只看车头我都看得出来。
对对对，但是我只能看出来这是21款的。哦，是个3，看到了。明天 Future 绿的，看来游戏来吧700，可以了，批准了，批准了。
Alan 平时一天看几次股票的价格？我想问。
就想起来看一下，也没有记多少次。
就你平均有没有3次？
那肯定有啊，我看手机有的时候就会看一眼，因为有的时候上班比较无聊，对吧？
啊。
怎么看这个车是3和 Y？ 等会儿它这个中间的屏幕结束的时候，有一个把车停下来的那样的时候，车横过来就特别清晰的可以看到了。对，看到这个踏板是性能版，然后中间这个充电的模块呢是21的新款，之前20不是这个样子的。就在这里，3。老马还不来呀？你现在已经开始上课了吗？
还没有。
那
个9月7号开学，我现在是在隔离。加拿大入境以后需要隔离14天。
他有人强制隔离吗？
让你居家隔离，但是从来没有人来敲我的门。
对啊，你出去也没人知道，对吧？
但是我没有出去。
你还挺乖的。
我就觉得很恼火。 加拿大的特斯拉不是特别多，我从那个机场坐到汉密尔顿这边，只看到2辆特斯拉，不像在国内满大街都是特斯拉，你知道吗？不管你去任何一座就是比较大的城市，
国内特斯拉，上海就是挺牛的，我觉得。
对，不只是上海吧，就你在成都，或者是我在其他，包括我在沈阳啊这些地方。
对，我就说上海工厂嘛，就是直接铺开了卖。
反正特斯拉就特别多，你知道吧？有时候你过一个桥，你就来向的车里面都有6、7辆特斯拉。真的，特斯拉特别多。我反而到这个加拿大了有点不适应啊，感觉怎么这么多汽油车，你知道吗？因为国内现在品牌又多，你知道吧？很多电动车你都不认识是什么。
是的。
就除了那些蔚来、小鹏啊这些的，就是还比较出名嘛。然后还有一些很多都不认识的各种各样的电动车都有。
我现在芝加哥特斯拉也多，但是没有西雅图、没有加州多。我没蹭过后轮毂，但是我蹭过前轮毂，我觉得修了呢。香港现在特斯拉也越来越多，哎，迟早的事儿。
我觉得特斯拉可以做一个特斯拉指数，对吧？特斯拉越多的地方，就跟那个星巴克指数一样。现在目前来看，越发达的地方，特斯拉应该越多。
是的，差不多，或者是跟天气、温度有关系。
啊，也有可能，确实。
美东少得可怜，不要急，等那个Austin 下线了。现在主要是造不出来，我周围好几个朋友订车，我等了好久啊，但是他们都挺有耐心的，一直在等。
对啊，现在我感觉国内和美国这边差距好大呀！美国现在订车要老马来了。
哦，可以。
那我闭麦了。
好的。
Sorry, I had some technical difficulties. We need AI for this. So, what we want to show today is that Tesla is much more than an electric car company. That we have deep AI activity in hardware on the inference level, on the training level, and basically, I think we're arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And this is a particular application of AI, but I think there are more applications down the road that will make sense. And we'll talk about that later in the presentation. But yeah, we basically want to encourage anyone who is interested in solving real-world AI problems at either the hardware or the software level to join Tesla, or consider joining Tesla. So let's see, we'll start off with Andre. Yep. Great. Give you mine.
Sound like it? Okay, hello. Great. Okay, hi everyone. Welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under the hood components that go into making a car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on. So here I'm showing a video of, actually, hold on. Apologies. So here I'm showing the video of the raw inputs that come into the stack, and then neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. Now, what I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all the electrical components, and for our purposes, the brain of the autopilot. And specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits the light, hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system.
大概意思就是
So the processing
重新
starts
建立了一个
when light hits
视
our
觉
cortical
还有神经
retina.
系统的
And
人
we
的
are
大
going
脑
to
一样。
process this information with neural networks. Now I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway. And so it had to keep lane, and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now, the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now, these RegNets give us, as an output, a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and have a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs. And they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFPN and a feature fusion across scales, we then go into task-specific heads. For example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly we converge in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, HydraNets, and these are the heads of the Hydra.
HydraNets.
Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks. So we can individually work on every one task in isolation. And for example, we can we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate.
就是说，同样一个东西到他面前，他需要做不同的事情，同时来操作，要保证路线，还有一看到红绿灯，还要来识别这些物体。
From the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these HydroNets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the HydroNet. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is someone in the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with the setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside the neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. So
就是早期的图片转换成可以识别的信号非常的糟糕，上面是看到的，下面是转换成的。
And so you can imagine just how high of a bar it is to predict that depth so accurately in these in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are two problems with this. Problem number one, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number two, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling in images and so
vector
on
space 怎么翻译啊？
vector space labels. We're going to talk a lot more about problem number 2 later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number 1. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images, and the evidence for whether or not this is a curve may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And
谁能看懂这个公式？
it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values, and then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff, and that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right about
现在讲如何把这个摄像头更好的给它
it translates all of the images into a virtual
校对。
camera. So if you were to average up a lot of repeater images, for example, which face to the back, you would, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions
好了，这就是
out of the neural net. This is a
讲了一大堆的结
multi-camera
果
network，
从刚才一开始只能看到一些
You can see that it's basically night and
线，
day.
现在可以看到
You can actually drive on this.
要走的路线的
And,
周围的这么
sometime
一些
some engineering
边缘。
And incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context. And we need to somehow figure out how to feed this into
现在又遇到
So in
新的
particular,
问题
is this car，
内
parked
存
or
不
not?
够。
Is it moving? How fast is it moving? Is it still there even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very
尤其在
helpful to
预
know
测
the
方面
signs or the road markings that I saw
需要
years ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. and then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time, and the kinematics of how the car has moved, and the positional encodings, and that's being concatenated, encoded, and stored in the feature queue. And that's going to be consumed by a video module. Now, there's a few details here, again, to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time, and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue, where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers, in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization of training this neural net. You can see that some of the channels are keeping track of different aspects of the road. Like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here. And basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network.
头已经开始疼了。
Seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us.
别急 ，AK 肯定都得讲晚上怎么回事，纯视觉怎么回事。
So that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly
对
looks like today.
我也是准备等
So,
James 走嘛。
We have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through regnets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFDN. This goes through a transformer module to re-represent it into the vector space and the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the Spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in the top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very
拿
strict
出来
latency
讲的肯定不
requirements,
怕
so this is
抄
not
啊，你
ideal.
随便
We are
抄，你
looking
要能
to
抄明白，算你
calculate
厉害。
just the sparse structure of the road, maybe like point by point, or in some other fashion that is that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run plane and control on top of it.
都不用说车企，哪个科技公司能搞出这种 event 呀？
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving. Then the car has to respond to all of cuttons and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high-dimensional.
笑死了。
What I mean by non-convex is There can be multiple possible
不是
solutions.
这
that can be
印度口音，
depending
我是
on
真的
but
听不
getting a
清楚。
globally consistent solution is pretty tricky. So there can be pockets of local minima that
我连
the
听英
planning
文都
can
听不懂，
get
现
stuck
在就
into.
别说他
And
讲这些
secondly,
词汇了
the。high dimensionality comes because the car needs to plan for the next 10 to 15
我先
seconds.
吃口
It
饭，
needs
太
to
饿
produce
了。
the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime.
不行，我听就想笑。
Discrete search methods are really great at solving non-convex problems because they are discrete. They don't get stuck in local minima. Whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete. It does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory.
不是咖喱饭，不是咖喱
Let's see an
饭。
example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change bit late, so it speeds up, goes behind the other car, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all
每
physics-based
1.5
models,
毫秒
these
可以做
features are very easy to
2500个
simulate,
搜索，
and in the end,
太
we
屌
have a
了
set。of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily
牛
making the
肉。
turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly.
不
and
光
optimize
要
for
预
the
测
overall
或者
scene
是规划
traffic
自己
flow.
的路线，还要规划我们周围的
In order
人
to do this, what we
所有
do
的
is
路
we
线。
literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now.
哦，
vehicle
对
has
面
high
来车情况下怎么
velocity,
办？
and like I said earlier, we
已
literally
经
run
来
the
了一
autopilot
辆，现在
planner
又来了一
for the
辆。
other object. So in this case, we run the planner for them. That object's plan now goes around their
我
part,
们要
their
预
side's
测
parked
这个第二
cars,
辆车的
and
轨
then after
迹
they。pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, okay, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield
哦，
to
我
us
们给他
based
挪
on
路
their yaw rate
那个人
and
走
their
了
acceleration.
他就开始
Autopilot
马上
immediately
做出
changes
判
its
断
mind。and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up, here on the right side, the green plot. There's a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it looked like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So this is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice-based search. And the heuristic here is a distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes. Obviously, this is a terrible heuristic. We want to do better than this. So if you added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's a collision, and if it's a collision, back up.
Summon mode 召唤模式时候经常看到那个现象，就是左右摆头，左右摆头。
We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function,
又来了蒙特卡罗的这个
search,
树状图。
this would only be effective for the single cone. But what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produces a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, etc. that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to collisions, comfort, traversal time, etc. But they can also be interventions from the actual manual driving events. We trained such a network for this simple parking problem. So here again, same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting stuck in any local minima. So this only takes 288 nodes and is several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution.
这个 neural net planner
optimize end-to-end, both with explicit cost functions and human intervention and other imitation
之前没
data.
有讲过。
This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks. And for training these networks, we need large data sets. I invite Andre to speak briefly about manual labeling.
AK 回来讲人工标注，然后上面讲自动标注，这有意思。
Yeah, so the story of data sets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, it's not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them. Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved. Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets.
3年前是第三方的人来做这个
party to get data sets for something this critical
标注
was just not going to cut it. The latency of working with a third party was extremely high. And,
但是延迟就很高，就是你要把东西发给他们，他们才能给处理好再发回来。特斯拉我们自己来做标注。
Data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the U.S. and co-located with
有
engineers.
1000个人来做这个数据的标注。
all of the infrastructure for them from scratch ourselves. So we have a team we are going to meet later today. That develops
1000个人只来做标注，同志
So
们。
here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space.
一开始呢，只是在照片的二维空间，
an image like this, and this is what it looked like, where we are
这个就很难看到这个物体和你的这个深度和距离。
As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional.
然后开始进化到 3D 和甚至 4D 的
vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And
20块1小时怎么可能啊？
changing the labels directly in vector space, and then we are
现在服务员都30-40块钱1小时吧。
So we're labeling directly in vector space, and this gave us a massive
这
increase
人工可贵了。
for a lot of our labels because you label once in 3D and then you get to reproject. But even this, we realized was actually not going to cut it. So because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto labeling, which is some of the infrastructure we've developed for labeling these clips.
下面讲自动标注，牛了牛了。
Hi again.
他又回来了
So。even though we have lots of human labelers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data like videos, IMU data, GPS, odometry, etc. These can be 40 per second to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers where we run a lot of neural networks offline to produce intermediate results like segmentation mask, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. One of the first tasks we want to label is the road surface. Typically, we can use splines or meshes to represent the road surface, but those are because of the topology restrictions are not differentiable and not amenable
来
to
分辨这个路上
So what
的
we do instead is
这个
inside
表面的
of neural
材质
network fields
surface
work from last year,
which is
就是
quite
柏油
popular.
路啊
So we use
还有
implicit representation to
路
represent
牙
the
子
road
呀，
surface.
还有什么人行横道啊
We are querying XY points on the ground and asking for the network to predict the height of the ground surface along with various semantics such as curbs, lane boundaries, road surface, drivable space, etc. So given a single XY, we get a Z. Together these make a 3D point and they can be reprojected into all the camera views. So we make millions of such queries and get lots of points. These points are reprojected into all the camera views. We are showing on the top right here one such camera image with all these points reprojected. Now we can compare this point, reprojected point with the image space prediction of the segmentations. And jointly optimizing this over all the camera views, both across space and time, produces an excellent reconstruction. Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road.
送他个禁言套餐。
Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HD maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras.
连墙障
The
碍
main
物全
innovation
都
here
能
is the density of the
画
point
出
cloud.
来。
Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate
这
arbitrary
个做的是太好
obstacles
看了。
that we can see in the world. One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is.
哎，这个
But
视频好
here,
像是芝加哥的。
we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics.
他说最重要的
velocity,
是
acceleration,
hindsight，
etc.
就是可以向回
One more
看，
advantage is that we can have like
就
different
是类似
tracks, but you
总
can
结的那种
systematically
感觉，
use
就像我们
conclusions,
回去会思
because
考
we know in
反
the
思
future
那
we
种
have
感觉
future。tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they are occluded. So this is a massive advantage. Combining everything together, we can produce these amazing data sets that annotate all of the road texture,
哇，
all of the static
你看
objects,
周围的人
and all
啊
of，the moving objects, even through occlusions, producing
全都给自动标
excellent
注好了，
labels.
牛。
You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have this zero velocity, so we can also know that they are parked. So this is huge for us.
这个街头有点像印
This is
度
one
啊，
more example of the same thing. You can see how everything is consistent. We want to produce a million such labeled clips and train our video, multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car. We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this
下面就
because
讲
of the
移
lack
除
of
雷达
data
之
in
后，
conditions.
纯视觉是怎么来解决的？你看这个雪，
So what we did, we asked the fleet to produce lots of similar clips, and the fleet responded, it did. So
So it produces it produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this.
不知道怎么解决的，反正就挺厉害的。
Cybertruck into a data set for the remove the radar. Can you all guess where we got this clip from? I'll give you a moment.
哎，这不 Cybertruck 吗？
Someone said it. Yes, yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty.
哦，这个是 CG 啊，这是动画。
So yeah.
做这么
In
真。
addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the same scene as seen before, but from a different camera angle. So a few things that I wanted to point out. For example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is Autopilot. Actually, Autopilot is driving that car, and it's making unprotected left turn. And since this is simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. So when does simulation help? It helps, number one, when the data is difficult to source. As large as our fleet is, it can still be hard to get some crazy scenes, like this couple and their dog running on the highway, while there are other high-speed cars around. This is a pretty rare scene, I'd say, but still can happen, and Autopilot still needs to handle it when it happens. When data is difficult to label, there are hundreds of pedestrians crossing the road. This could be a Manhattan, downtown, people crossing the road. It's going to take several hours for humans to label this clip. And even for automatic labeling algorithms, this is really hard to get the association right, and it can produce like bad velocities. But in simulation, this is trivial because you already have the objects. You just have to like spit out the cuboids and the velocities. And also, finally, when we introduce closed-loop behavior, where the cars needs to be in a determined situation, or the data depends on the actions, this is pretty much the only way to get it reliably. All this is great. What's needed to make this happen? Number one, accurate sensor simulation. Again, the point of the simulation is not to just produce pretty pictures. It needs to produce what the camera in the car would see and other sensors would see. So here, we are stepping through different exposure settings of the real camera on the left side and the simulation on the right side. We're able to pretty much
对，
match
即时
what
渲
the
染
real
这个
camera
翻译的好。
In order to do this, we had to model a lot of the properties of the camera in our sensor simulation, starting from sensor noise, motion blur, optical distortions, even headlight transmissions, even like diffraction patterns of the windshield, etc. We don't use this just for the Autopilot software. We also use it to make hardware decisions such as lens design, camera design, sensor placement, even headlight transmission properties. Second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of pains to produce nice spatio-temporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic. Yeah. In addition, we also use ray tracing to produce realistic lighting and
这个
global
渲染做的
illumination.
太屌了。
Okay, that's the last of the cop cars, I think. We obviously cannot have really just 4 or 5 cars because the network will easily overfit because it knows the sizes. So we need to have realistic assets like the moose on the road here. We have thousands of assets in our library. and they can wear different shirts and actually can move realistically. So this is really cool. We also have a lot of different locations mapped and created to create these sim environments. We have actually 2,000 miles of road built, and this is almost the length of the roadway
我
from
现
the
在
east
就
coast to
是
west coast of the United
整
States.
个已经
I think
建立一
it's
个
cool.
虚拟的
In
道
addition,
路
we
啊、
have
人
built
啊，
efficient
还有
tooling to build
车呀
several miles
然后
on a single day
你可以
for
让
a
你
single
设计
object.
出来的车就在这里跑就可以了。
But this is just tip of the iceberg. Actually, most of the data that we use to train is created procedurally using algorithms as opposed to artists making these simulation scenarios. So these are all procedurally created roads with lots of parameters such as curvature, varying trees, cones, poles, cars with different velocities, and the interaction produce an endless stream of data for the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects.
哦
With this combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of
哎，
it.
这个谁能帮我理解一下？
Then
这个
when
不
we
是
recreate autopilot on it,
用
autopilot
特
can
斯
do
拉
entirely new
在
things
做
and we
高
can
精
form
地
new
图吗？
worlds, new outcomes from the original failure.
他用所有的
This is
车
amazing
拍到的
because
视
we
频，
really
把
don't
它们
want
组合成
autopilot
一
to fail
起，
and when it fails,
成了这么一个
we
虚拟的
capture
世
it,
界。
and keep it to that bar.
没太懂。
Not just that, we can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. This is a result from last night because it was cool and we wanted to present it. But yeah, I'm very excited for what Sim can achieve. But this is not all bullshit because networks trained in the car already use simulation data. We used 300 million images with almost 500 million labels. And we want to crush down all the tasks that are going to come up for the next several months. With that, I invite Milan to explain how we scale these operations and really build a label factory and spit out millions of labels.
哇，这个想法真的太屌了。
Hey everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. And so in the specific context of the push we went through as a team here a few months ago to get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute.
大家想一下，这个街上的车越来越多，它能造到这个虚拟的这个东西，就越来越快，越来越大。
idea of what it takes to take our neural networks and
太牛了。
move them in the car. And so the two main constraints that we're working under here are mostly latency and frame rate, which are very important for safety, but also to get proper estimates of acceleration and velocity of our surroundings. And so the meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And we do that while figuring out a schedule that's optimized for throughput while working under severe SRAM constraints. And so, by the way, we're not doing that just on one engine, but across two engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle. while the other one is
一个做视觉规划，一个做视觉规划和
both at the
也
hardware
对，
and software level.
都有做 control。
So how do we iterate quickly together as a group through these AI development cycles? Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million
每一
evaluations
周
per week
可以
on eco change
测试100 多
that the team is
100万次以
producing.
上。
And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated
有
cluster.
3000个 full self-driving 的 computer 专门来
So on
跑
top
这些
of
东
this,
西
we've。been developing really cool debugging tools. And so here is a video of one of our tools, which is helping developers iterate through the development of neural networks and comparing live the outputs from different revisions of a same neural network model as we're iterating live through video clips. And so last but not least, we've been scaling our neural network training compute dramatically over the past few years. And today we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
哇，
Thank you, Milan. My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of
哦
the
讲 Dojo 了，
multidisciplinary Tesla team that is working on this
超级计算机，世界排
As
名
we
的
saw
啊。
from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer. And that's how we started.
主播已经放弃了，翻译不过来，看不懂。
Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same
哦，
time.
目标是达成最
We
强
thought
的
about how to
人工
build
智能训练
it.
的
We
系
came
统
up。with a distributed compute architecture.
这
After
种
all,
分配
all the
式
training
的
computers out
这
there
个
are
架构。
distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a two-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And onto this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here. We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, 1 cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8.
反正就是高宽带、低延迟。
1.25 megabyte of fast ECC protected SRAM and the low latency high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. So let's look at the
这还是
architecture.
最小的那么一个单
The
元。
computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. It is a superscalar in-order CPU with 4 wide vector and 4 wide scalar and 2 wide vector pipes. We call it in order, although the vector and the scalar pipes can go out of order, but for the purists out there, we still call it in order. And it also has 4-way multi-threading. This increases utilization because we can do compute and data transfers simultaneously. And our custom ISA, which is the instruction set architecture, is fully optimized for machine learning workloads. It has features like
四路
transpose,
多线
gather,
程。
link traversals, broadcast, just to name a few. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. And network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training optimized chip, our D1 chip. This chip is manufactured in 7 nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon, there is no legacy support. This is a pure machine learning machine. And this is the D1 chip in a flip chip VGA package. This was entirely designed by Tesla team internally,
他手
all
里
the
这个
way
小芯片
from the architecture to GDS out and package.
太牛了。
This chip is like a GPU level compute with a CPU level flexibility
GPU
and twice the
的
network
算力
chip
和
level
CPU
I/O
的
bandwidth.
这
If I
个
were to plot
flexibility
the I/O
兼容
bandwidth
性
on
啊
the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why
特
our
斯拉
design
做这个
point
第一
excels
芯片，
beyond
那
par.
苹果的 M1 芯片，
Now that we had this
英伟达
fundamental
AMD 的
physical
芯
building
片
block,
会不会 有
design the
有点危
system
险，
around
我
it.
靠，
Let's see.
这是什么鬼？
Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put
我的天！我的天呐！
500,000 training nodes together
50万个
from
训练的节
our
点。
compute plane. This is 1,500 D1 chips seamlessly connected to each other.
50万个这个第一芯片组成的这个Dojo，
We add Dojo interface processors
我
on
的
each
妈
end.
呀！
This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training
这
tile.
是什么呀？
And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module. It was not
这
easy
是
to design
整
this.
个
There
做
were
芯
no
片行业
tools
可能是
that
最大的一个
existed.
MCM。
All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here, but we didn't stop here. We integrated
我的天！
entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated,
哇，
interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering.
我的天呐！
Our compute
这个就
plane
是一开始宣传那个海报吗？
orthogonal
这也太酷了！
power supply and cooling.
这也太酷了！
High bandwidth compute planes possible.
哎，这比什么苹果发布会爽多了！你敢想这是一个车企的发布会
9
吗？
petaflop training tile. This becomes our unit of scale for our system. And this is real.
哇！这个芯片，我的天哪！我的天哪！
I can't believe I'm holding 9 petaflops out here.
他手里拿这个算力，可能超过很多国家的算力都有可能。
And in fact, last week we got our first functional training tile. And on a limited
拿这个去
cooling
跑分儿，我
benchtop
的天！
setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, This is MinGPT-2 running on Dojo. Do you believe it?
GPT。我操！
Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tile together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through.
我看了真的热血沸腾，你
There's
知道
no
吗？
bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this,
我的天，可以无限的延伸。
we have an exapod.
Exapod， 这都什么东西啊
1 exaflop of compute in 10 cabinets.
？What the fuck？
It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node.
这是什么东西啊？
Out here with uniform bandwidth.
疯了我！
Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo Processing Unit. A DPU consists of 1 or more D1 chips. It also has our interface processor and 1 or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network.
DPU Dojo Processing Unit， 全是新词
What
儿
does。the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping.
这个真的做出来就直接可以卖它的算力了，帮别人训练。这个就是 AWS 那种的，直接把 CUDA 变成 Dojo 就可以了。
Uses multiple techniques to extract parallelism. It can transform the networks to achieve not only fine-grained parallelism using data model graph parallelism techniques, it also can do optimizations to reduce memory footprints. One thing, because of our high bandwidth nature of the fabric is enabled out here, is model parallelism could not have been extended to the same level as what we can. It was limited to chip boundaries. Now we can, because of our high bandwidth, we can extend it to training tiles and beyond. Thus, large networks can be efficiently mapped here at low batch sizes and extract utilization and new levels of performance. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. And our compiler engine is just part of our entire software suite. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to.
PyTorch.
And our compiler generates code on the fly such that it could be reused for subsequent execution. It has
靠，
a
连软件
LLVM
都
backend
给
that
你
generates the binary
铺设
code
好了。
And this ensures we can create optimized code for the hardware without relying
这个
on
真是
even
放
single
大大
line
大招啊！
of handwritten kernel. Our driver stack takes care of the multi-host, multi-partitioning that you saw a few slides back. And then
真的，
we also have profilers and debuggers in our software stack. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how We got modularity up and down the stack to add to new levels of
从
performance.
硬件到系统到芯片、软件，
It will be. It will be a
整个
fastest AI
全
training
部
computer
都提高的
4x
算力
the
和运
performance
行
at
速
the
度，
same cost.
会上是世界上最快的人工智能训练的这么一个机器，这就是 Dojo。这么强算力，它直接卖 service， 哇，那特斯拉估值就全变了呀！这么强的算力。
And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about
下一
10x
代
more with
是
different
这一代的
aspects
Dojo
that
的
we can
10
do
倍的
all
进
the way
步。
from silicon to the system again. We will have this journey again. We are recruiting heavily for all of
将来
these.
真的就是建好了在家里卖服务就可以了。将来自动驾驶解决之后，这些算力不会就没了，会一直在加的，就是你的矿机。你知
And
道吗
next up, Elon will update us on what's beyond our vehicle fleet for AI.
哦，现在开始讲 Beyond Vehicle Fleet，就是我估计就讲 AWS 那种嘛，就可以。我操，这不会是机器人吧？我操！机器人！What the fuck！ 哇！我操！哇！Oh my god！ 这是人在里面吧？这是人在里面啊！我操！不是机器人。
All right. Thank you.
那白高兴了。
Now, unlike Dojo, obviously that was not real. So Dojo is real. The Tesla bot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world. It kind of makes sense to put that onto a humanoid form. And we're also quite good at
但是老马
sensors
说
and
这个将来
batteries
会是
and
真的，这也印证了我那个视频。
So we think we'll probably have a prototype sometime next year. That,
明年，
is,
明年
looks
会有
like
样
this.
机。
And it's
牛了，
intended
牛了，牛了。
to be friendly, of course, and navigate through a world built for humans, and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it, and most likely overpower it. So hopefully that doesn't ever happen, but you never know. So it's it'll be a light, yeah, anyway, 5 miles an hour. If you can get run faster than that, you'll be fine. So yeah, it's around 5'8". Has sort of a screen where the head is for useful information. but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and yeah.
Wow.
Full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, you know, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that.
Neural network,
it should be able
neural
to,
net planning,
please go to the store and get me the following groceries, that kind of thing.
自动驾驶的芯片。
Yeah, I think we can do that.
Wow.
And yeah, this I think will be quite profound, because if you say, like, what is the economy? It is at the foundation, it is labor. So what happens when there is, you know, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute. So yeah, but I think it's essentially in the future, physical work would be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy, because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. So yeah. Join our team and help build this.
快点加入特斯
I'll
拉
have。everyone come back on the stage, and you guys can ask questions if you'd like.
加入特斯拉。对。Maybe try to get the camera angle from there, not from the side. All right, cool. So we'll probably turn the lights back on, and yeah, great. So we're happy to answer any questions you have about anything on the software, hardware side, where things are going, and yeah, fire away. We have, because the lights are like interrogation lights, we actually cannot see. Ah, there we go. Great. Oh. All right, cool.
I can just, okay, there we go. First off, I mean, thanks to all the presenters. That was just super cool to see everything. I'm just curious at a high level, and this is kind of a question for really anyone who wants to take it. To what extent are you interested in publishing or open sourcing anything that you do for the future?
大家看老马的肚子好可爱。
Well, I mean, it is fundamentally extremely expensive to create the system, so somehow that has to be paid for. I'm not sure how to pay for it if it's fully open sourced. Yeah, unless people want to work for free. But I should say that this is, if other car companies want to license it and use it in their cars, that would be cool. This is not intended to be just limited to Tesla cars.
老马说了，其他车企要想用我们的技术，我们也会开放的。
supercomputer. So did you solve the compiler problem of scaling to these many nodes, or if it is solved, is it only applicable to Dojo? Because I'm doing research in deep learning accelerators, and getting the correct scalability or the distribution, even in one chip, is extremely difficult from the research project's perspective. So I was just curious.
Excuse me, mic for Bill. You want to?
Have we solved the problem? Not yet. Are we confident we will solve the problem? Yes. We have demonstrated networks on prototype hardware now. We have models, performance models showing the scaling. The difficulty is, as you said, how do we keep the localities? If we can do enough model parallel, enough data parallel to keep most of the things local, we just keep scaling. We have to fit the parameters in our working set in our SRAM that we have, and we flow through the pipe. There's plenty of opportunities. Sorry, as we get further scale for further processor nodes, have more local memory trade-offs with bandwidth, we can do more things. But as we see it now, the applications that Tesla has, we see a clear path.
And our modularity story means we can have different ratios, different aspects created out of it. I mean, this is something that we chose for our applications internally.
Sure.
The locality portion of it, given that training is such a soft scaling application, even though you have all this compute and have a high bandwidth interconnect, it could not give you that performance because you are doing computations on limited memory at different locations. So I was that's very curious to me when you said it's solved, because I just jumped onto the opportunity and would love to know more, given that how much you can open source.
Yeah.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. I mean, fundamentally, this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration. And so if you can reduce the time between iterations, the rate of improvement is much better. So if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal. But the acid test here, and what I've told the Dojo team is like it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful. So.
Hi, right over here. Love the presentation. Thank you for getting us out here. Love everything, especially the simulation part of the presentation. I was wondering, it looked very realistic. Are there any plans to maybe expand simulation to other parts of the company in any way?
Hi, I'm Ian Glow. I manage the autopilot simulation team. So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So I want to expand, or we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the Tesla bot.
Oops.
Optimus.
Optimus subprime.
Yeah. Hi, this is Ali Jahanian. Thank you for the great presentation and putting all of these cool things together. Yeah, for a while I have been thinking that the car is already a robot. So why not a human robot? And I'm so happy that today you mentioned that you are going to build such thing. Especially I think that this can give opportunity for ways of putting multi-modality together. For instance, we know that in the example that you showed that there was a dog and with some passengers or running together. The language and symbolic processing can really help for visualizing that. So I was wondering if I could hear a little more about this type of putting modalities together, including language and vision. Because I have been working with, for instance, mini GPT that Andre put out there. And yeah, I didn't hear much about other modalities that's going into the car, or at least in the simulation. Is there any comment that you could tell us?
Well, driving is fundamentally basically almost entirely vision neural nets. Basically, it's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. So there is some amount of audio. You want to hear if there's like emergency vehicles, or I guess converse with the people in the car. If somebody's yelling something at the car, that the car needs to understand what that is. So all the things that are necessary for it to be fully autonomous. Yeah. Thank you.
Hi, thank you for all the great work that you've shown. My question is for the team, because the data that was shown seems to be predominantly from the United States that the FSD computer is being trained on. But as it gets rolled out to different countries, which have their own road systems and challenges that come with it, how do you think that it's going to scale? Like I'm assuming the ground up is not a very viable solution. So how does it transfer?
现在问自动驾驶到其他国家该怎么铺设
Well, we actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the U.S. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, let's not add additional complexity right now. Let's just solve it for the US, and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
Yeah, I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and then there's the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. Even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
And I want to ask that when you do the photometric process, multi-view geometry, how much of an error do you see? Is it like 1 millimeter, 1 centimeter? So I'm just, if it's not confidential.
Sorry, the question, what is the resolution?
What's the difference between the synthetic? Check. What is the difference between the synthetically created geometry to the actual geometry?
Yeah, it's usually within a couple centimeters, 3 or 4 centimeters. That's the standard deviation.
with different kind of modalities to bring down that error?
We primarily try to find scalable ways to label. In some occasions, we use other sensors to help benchmark, but we primarily try to use cameras for this system.
Okay, thanks.
Yeah, I mean, I think we want to aim for the car to be positioned accurately to the sort of centimeter level, you know, something on that order.
Obviously, it will depend on distance. Like close by things can be much more accurate than farther away things, and they would matter less because the car doesn't have to make decisions much farther away. And as it comes close, it will become more and more accurate.
Exactly. A lot of questions.
Thanks, everybody. My question has to do with sort of AI and manufacturing. It's been a while since we've heard about the alien dreadnought concept. Is the humanoid that's behind you guys, is that kind of brought out of the production hell timeline and saying that humans are underrated in that process?
Well, sometimes like you know, something that I say is taken to too much of an extreme. There are parts of the Tesla system that are almost completely automated, and then there are some parts that are almost completely manual. If you were to walk through the whole production system, you would see a very wide range from, yeah, like I said,
那个声音还真挺像 Rob 的，
automatic
不知道是不是他。
to almost completely manual. But the vast majority, most of it is already automated. And then with some of the design architecture changes, like going to large aluminum high-pressure die-cast components, we can take the entire rear third of the car and cast it as a single piece. And now we're going to do the front third of the car as a single piece. So the body line drops by like 60 to 70% in size. But yeah, the robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot. So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it. And make sure it's safe.
这个机器人影响好
Just
深
say,
远
like,
啊。
also, volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. It's also important for the humanoid robot. Like, how do you make the humanoid robot not be super expensive? And you know.
Hi. Thank you for the presentation. And my question will be about scaling of Dojo. And in particular, how do you scale the compute nodes in terms of thermals and power delivery? Because there is only so much heat that you can dispense and only so much power that you can bring to like cluster rack. And how do you plan to scale it? And how do you plan to scale it in multiple data centers?
Sure. You want to take it? Oh, yeah.
Yeah, hi. I'm Bill. I'm one of the Dojo engineers. So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw in the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so when we talk about clicking these together, once we click it to power and once we click it to cooling, it will be fully powered and fully cooled. And all of that is less than a cubic foot.
Yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle and applied that to the supercomputer. Because as you point out, getting heat out is extremely important. It's just really heat limited. So, yeah, so it's funny that like at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
Hi. My question is also similarly a question of scaling. So it seems like a natural consequence of using, significantly faster training hardware is that you'd be either training models over a lot more data, or you'd be training a lot more complex models, which would be potentially significantly more expensive to run at inference time on the cars. I guess I was wondering, if there was a plan to, also apply Dojo as something that you'd be using, on the self-driving cars, and if so, do you foresee additional challenges there?
So as you could see, Andre's models are not just for cars. There are auto labeling models, there are other models that are beyond car application, but they feed into the car stack. So Dojo will be used for all of those too, not just the car inference part of the training.
Yeah, the Dojo's first application will be consuming video data for training that would then be run in the inference engine on the car. But and that I think is an important test to see if it actually is good, but is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So CPUs and GPUs, they're not made to be. They're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically GPUs are still essentially running neural net training in emulation mode. So with Dojo, we're saying okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
Hey, I have a question here. Hi. So you described two separate systems. One was for vision, other was for planner and control. Does Dojo allow you to train networks that cross that boundary? And second thing is, if you were able to train such networks, would you have the onboard compute capability in the FSD system to be able to run that under your tight latency constraints? Thanks.
Yeah, I think we should be able to train planner networks on Dojo or any GPUs. It's really invariant to the platform. And I think if anything, once we make this entire thing end-to-end, it will be more efficient than decoding a lot of these intermediate states. So we should be able to run faster if you make the entire thing end-to-end neural networks. We can avoid a lot of decoding of these intermediate states and only decode the essential things required for driving the car.
Yep. Certainly, end-to-endness is the guiding principle behind a lot of the network developments. And over time in the stack, neural networks have taken on more and more functionality. And so we want everything to be trained end-to-end because we see that works best. But we are building it incrementally. So right now, the interface, there is vector space, and we are consuming it in the planner, but nothing really fundamentally prevents you from actually taking features and eventually fine-tuning end-to-end. So I think that's definitely where this is headed.
Yeah. And the discovery really is what are the right architectures that we need to place in network blocks to make it amenable to that task. So like Andre described, we can place spatial RNNs to help with the perception problem. And now it's just neural network. So similarly for planning, we need to bake in search and optimization into the network architecture. And once we do that, you should be able to do planning very quickly, similar to C++ algorithms.
Okay. I think I had a question very similar to what he was asking about. It seems like a lot of neural nets are around computer vision. And kind of traditional planning, you had model predictive control and solving convex optimization problems very quickly. And I'd wonder if there's a compute architecture that's more suited for convex optimization or the model predictive control solutions very quickly.
Yeah, 100%. We want to bake in, like I said earlier, we want to bake in these architectures that do, say, model predictive control, but it just replace some of the blocks with neural networks. Or if we know the physics of it, we can also use physics-based models, part of the neural networks, forward pass itself. So we are going to go towards a hybrid system where we will have neural network blocks placed together with physics-based blocks and more neural networks later. So it will be a hybrid stack, and what we know to do well, we place it explicitly, and what the networks are great at, we'll use the networks to optimize this. So build an end-to-end stack with this architecture baked in.
I mean, I do think that so as long as you've got like surround video neural nets for understanding what's going on and can convert the surround video into vector space, then you basically have a video game. And if it's like if you're in Grand Theft Auto or whatever, you can make the cars drive around and pedestrians walk around without crashing. So you can do. You don't have to have a neural net for control and planning, but it's probably ultimately better. But I think you can probably get to. In fact, I'm sure you can get to much safer than a human with control and planning, primarily in C++ with perception, vision in neural nets.
Hi. My question is, we've seen other companies, for example, use reinforcement learning and machine learning to optimize power consumption in data centers and all kinds of other internal processes. My question is Tesla using machine learning within its manufacturing design or other engineering processes?
I discourage use of machine learning because it's really difficult. Unless you have to use machine learning, don't do it. It's usually a red flag when somebody says, we want to use machine learning to solve this task. I'm like, that sounds like bullshit. So
老板说，如果有个人让你用人机器学习解决一个问题，然后他劝你还是不要做了，因为他觉得99%都是扯淡。
You reach for machine learning when you need to, but I've not found it to be a convenient, easy thing to do. It's a super hard thing to do. Now, that may change if you've got a humanoid robot that can, understand normal instructions. But yeah, generally minimize use of machine learning in the factory.
Hi. Based on your videos from the simulator, it looked like a combination of graphical and neural approaches. I'm curious what the set of underlying techniques that are used for your simulator and specifically for neural rendering, if you can share.
Yeah, so we're doing, at the bottom of the stack, it's just traditional game techniques, just rasterization, real time, very similar to what you'd see in like GTA. On top of that, we're doing real-time ray tracing, and then those results were really hot off the press. We had that little asterisk at the bottom that was from last night. We're going into the neural rendering space. We're trying out a bunch of different things. We want to get to the point where the neural rendering is the cherry on the top that pushes it to the point where the models will never be able to overfit on our simulator. Currently, we're doing things similar to photorealism enhancement. There's a recent paper enhancing photorealism enhancement, but we can do a lot more than what they could do in that paper because we have way more labeled data, way more compute, and also we have a lot more control over our environments. And we also have a lot of people who can help us make this run at real time. But we're going to try whatever we can do to get to the point where we can train everything just with the simulator if we had to, but we will never have to because we have so much real-world data that no one else has. It's just to fill in the little gaps in the real world.
Yeah, the simulator is very helpful when there's like these rare cases like collision avoidance right before an accident. And then, ironically, the better our cars become at avoiding accidents, the fewer accidents there are, so then our training set is small, so then we have to make them crash in the simulation. So it's like, okay, minimize potential injury to pedestrians and people in the car. You have 5 meters, you're traveling at 20 meters per second. What actions would minimize probability of injury? We can run that in Sim. So, cars driving down the wrong side of the highway, that kind of thing. Happens occasionally, but not that often.
For your humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenge is. are in that context to make this viable?
Well, I think for the Tesla bot, Optimus, it's basically going to start with just dealing with work that is boring, repetitive, and dangerous. Basically, what is the work that people would least like to do?
Hi. So quick question about your simulations. Obviously, they're not perfect right now. So are you using any sort of domain adaptation techniques to basically bridge the gap between your simulated data and your actual real-world data? Because I imagine it's kind of dangerous to.
机器人有什么？机器人用处多了呀！你去看我这个7个月前的视频，讲了很多可以用的地方。就你能想象人不愿做的事情，机器人都可以去做。
I mean, we're producing the videos straight out of the simulator, the full clips with kinematics and everything.
最主要的还是去做 将来去火星上，对吧？
It's just a small targeted segment, and we only are evaluating based on real-world video.
机器人去那里干活，我觉得这是老马的最终极目的。现在在地球上很多事情都可以让机器人去做。
We will as we scale up the data. And that's what we're hoping to use neural rendering to bridge that gap, to push that even further out. We've already done things where we're using like the same network as in the car, but retrain it to detect sim versus real to drive our art decisions. And that's actually helped prevent some of these things as well.
Yeah, just to emphasize that overwhelmingly, the data set is the real video from the cars on the actual roads. Nothing's weirder or has more corner cases than reality. It gets really strange out there. But then if we find, say, a few examples of something very odd, and there's some very odd pictures we've seen, then in order to train it effectively, we want to create simulations, say 1,000 simulations that are variants of that quirky thing that we saw, to fill in some important gaps and make the system better. And really, all of this is about, over time, just reducing the probability of a crash or an injury, and just the march of nines. Like, how do you get to 99.9999999% safe? You know, and each 9 is an order of magnitude difficulty increase.
Hey all, thanks so much for the presentation. I was curious about the Tesla bot. Specifically, I'm wondering if there are any specific applications that you think the humanoid form factor lends itself to. And then secondary, because of its human form factor, is emotion or companionship at all thought about on the product roadmap at all?
Well, we certainly hope this does not feature in a dystopian sci-fi movie. But you know, like, really, at this point, we're saying, like, maybe this robot can we're trying to do as much as possible. Can it do boring, dangerous, repetitive jobs that people don't want to do? And you know, once we can have it do that, then maybe it can do other things too. But
先让机器人做那些无聊啊、危险啊、需要重复性的工作。
It could be your buddy too. I mean, if I want to have to be your
可以作为你的这个伙伴。Be your buddy.
I'm sure that people will think of some very creative uses.
可以想象出很多有创意性的用法。大家刚才说的什么女机器人什么的。
So firstly, thanks for the really incredible presentation. My question is on the AI side. So one thing we've been seeing is that with some of these language modeling AIs, we've seen that scaling has just had incredible impacts in their capabilities and what they're able to do. So I was wondering whether you're seeing similar kinds of effects of scaling in your neural networks and your applications.
Absolutely. A bigger network, typically we see it performs better, provided you have the data to also train it with. And this is also what we see for ourselves. Definitely in the car, we have some latency consideration to be mindful of. And so there we have to get creative to actually deploy much, much larger networks. But as we mentioned, we don't only train neural networks for what goes in the car. We have these auto-labeling pipelines that can utilize models of arbitrary size. So in fact, we've trained a number of models that are not deployable, that are significantly larger and work much better because we want 100%, we want much higher accuracy for the auto-labeling. And so we've done a lot of that, and there we definitely see this trend.
Yeah, the auto-labeling is an extremely important part of this whole situation. Without the auto-labeling, I think we would not be able to solve the self-driving problem.
It's kind of a funny form of distillation where you're using these very massive models plus the structure of the problem to do this reconstruction, and then you distill that into neural networks that you deploy to the car. But we basically have a lot of neural networks and a lot of tasks that are never intended to go into the car.
Yeah, and also, as time goes on, you get new frames of information. So you really want to make sure your computer is distributed across all the information as opposed to just taking a single frame and hogging on it for, say, 200 milliseconds. You actually have newer frames coming in, so you want to use all of the information and not just use that one frame.
I think one of the things we're seeing is that the car's predictive ability is eerily good. It's really getting better than human in terms of predicting, like you said, predict what this road will look like when it's out of sight, like it's around the bend, and it predicts the road with very high accuracy. Predict pedestrians or cyclists where behind, where it just sees a little corner of the bicycle and a little bit through the windows of the bus. And its ability to predict things is going to be much better than humans, like really way beyond.
Right. Yeah, we see this often where we have something that is not visible, but the neural network is making up stuff that actually is very sensible. Sometimes it's eerily good, and you have to you're wondering this is in the training set. And actually, in the limit, you can imagine the neural net has enough parameters to potentially remember Earth. So in the limit, it could actually give you the correct answer, and it's kind of like an HD map baked into the weights of the neural net.
Yeah.
I have a question about the design of the Tesla bot. Specifically, how important is it to maintain that humanoid form? To build hands with 5 fingers, that also respects the weight limits could be quite challenging. You might have to use cable driven, and then that also causes all kinds of issues.
I mean, this is just going to be bot version 1. I mean, we'll see. So it needs to be able to do things that people do, and be a generalized humanoid robot. I mean, you could potentially have it give it 2 fingers and a thumb or something like that. For now we'll give it 5 fingers and see if that works out okay. It probably will. It doesn't need to be have incredible grip strength, but it needs to be able to work with tools. So and carry a bag, that kind of thing.
Hi, thanks a lot for the presentation. So an old professor of mine told me that the thing he disliked a lot about his Tesla was that the autopilot UX didn't really inspire much confidence in the system, especially when objects are spinning, classifications are flickering. I was wondering, even if you have a good self-driving system, how are you working on convincing Tesla owners, other road users, and just the general public that your system is safe and reliable?
说如果你即使你的很好，你如何来告诉大众
A while back, cars used to spin. They don't spin anymore. If you've seen the FSD beta videos, they're pretty solid, and they will be getting more solid.
Yeah, as you add more and more data and train these multi-cam area networks, these are pretty recent, actually, just a few months old, and it's still improving. It's not a done product, and in our minds we can clearly see how this is just going to be perfect vector space, because why not? All the information is there in the videos. It should produce it given lots of data and good architectures. And this is just an intermediate point in that timeline.
I mean, it's clearly headed to way better than human, without question.
My turn? Oh, hi, here. I was wondering if you could talk a little bit about the short to medium-term economics of the bot. I guess I understand the long-term vision of replacing physical labor. I also think repetitive, dangerous, and boring tasks tend to not be so highly compensated. And so I just don't see how to reproduce the, start with a supercar and then break into like the lower end of the market. How do you do that for a robot humanoid?
Well, I guess you'll just have to see.
老马太狠了，人家问他你对机器人的进展，他说我们走着瞧吧。
I was curious to know how the car AI prioritizes occupant safety versus pedestrian safety, and what thought process goes into like deciding how to bake this into the AI.
Well, I mean, the thing to appreciate is that from the computer standpoint, everything is moving slowly. So, to a human, things are moving fast. To the computer, they are not moving fast. So I think this is, in reality, somewhat of a false dichotomy. Not that it will never happen, but it will be very rare. If you think of it as like, going the other direction, like rendering, with full ray tracing, neural net enhanced graphics on something like Cyberpunk or any advanced video game, doing 60 frames a second, perfectly rendered. Like, how long would it take a person to even render one frame, and without any mistakes? Can't be done. I mean, it would take like a month just to render one frame out of 60 in a second in a video game. It's computers are fast and humans are slow. I mean, for example, on the rocket side, you cannot steer the rocket to orbit. We actually hooked up a joystick to see if anyone could steer the rocket to orbit, but you need to react at roughly
拿火箭
6,
举例
7
子，
hertz. People can't do it.
说
Not
那
even
个
that's
进
pretty
轨
low,
道
you know.
人是做不到
We're
的。
talking more like aiming for like 30 hertz type of thing.
Hi, with the, over here, with hardware 3, there's been lots of speculation that with larger
有人问
nets,
hardware
it's
4.0
hitting
了。
the limits of what it can provide. How much headroom has the extended compute modes provided, and at what point would hardware 4 be required, if at all?
什么时候4.0？
Well, I'm confident that hardware 3 or the full self-driving computer 1 will be able to achieve full self-driving at a safety level much greater than a human, probably, I don't know, at least 200 or 300% better than a human. Then obviously there will be a future hardware 4 or full self-driving computer 2, which we'll probably introduce with the Cybertruck. So maybe in about a year or so. That is probably, well, that'll be about 4 times more capable, roughly. But it's really just going to be like, can we take it from, say, for argument's sake, 300% safer than a person to 1,000% safer? Just like there are people on the road who, with varying driving abilities, but we still let people drive. You don't have to be the world's best driver to be on the road. So, as we see. So, yeah. You guys want to say anything? All right.
So are you worried at all, since you don't have any depth sensors on the car, that people might try like adversarial attacks, like printed out photos or something to try to trick the RGB neural network?
Yeah, like what? Pull some like Wile E. Coyote stuff, like paint the tunnel on the wall. It's like, oops. We haven't really seen much of that. I mean, for sure, like right now, if you, most likely, if you had like a T-shirt with a T-shirt with like a stop sign on it, which I actually have a T-shirt with a stop sign on it, and then you like flash the car, it will stop. I proved that. But we can obviously, as we see these adversarial attacks, then we can train the cars to, notice that, well, it's actually a person wearing a T-shirt with a stop sign on it, so it's probably not a real stop sign. Yeah.
Hi, my question is about the prediction and the planning. I'm curious, how do you incorporate uncertainty into your planning algorithms? Do you just basically assume, you mentioned that you run the autopilot for all of the other cars on the road. Do you assume that they're all going to follow those rules, or are you accounting for the possibility that, well, they might be bad drivers, for example?
Yeah, we do account for multimodal futures. It's not that we just choose one. We account for, okay, this person can actually do many things. And we use their actual physics and kinematics to make sure that they're not doing a thing that would interfere with us before we act. So if there's any uncertainty, we are conservative and then would yield to them. Of course, there's a limit to this, because if you're too conservative, then it's probably not practical. So at some point, we have to assert. And even then, we make sure that the other person can yield to us and act sensibly.
I should say, before we introduce something into the fleet, we will run it in shadow mode, and we'll see what would this neural net, for example, have done in this particular situation. And then effectively, the drivers are training the net. So if the neural net would have controlled and say veered right, but the person actually went left, and it's like, oh, there was a difference. Why was there that difference?
Yeah, and secondly,
so
we also
all the human drivers are essentially training the neural net as to what is the correct course of action, assuming it doesn't then end up in a crash. It doesn't count in that case.
Yeah, and secondly, we have various estimates of uncertainty like flicker, and when we observe this, we actually say if you're not able to see something, we actually slow down the car to be, again, safe and get more information before acting. Yeah, we don't want to be brazen and just go into something that we don't know about. We only go into places where we know about.
Yeah, yeah. It should be like aspirationally, the car should be the less it knows, the slower it goes.
Yeah.
That's just
not true at some point, but now it's
improving. Should be speed proportionate to confidence.
Thanks for the presentation. So I am curious, appreciate the fact that the FSD is improving, but if you have the ability to improve one component along the AI stack that presented today, whether it is simulation, data collections, planning and control, etc., which one, in your opinion, is going to have the biggest impact for the performance of the full self-driving system?
It's really the area under the curve of just like multiple points, and if you improve anything, it should improve the area.
I mean, the short term, it's arguably, we need all of the nets to be surround video. And so we still have some legacy. This is very short term. Obviously, we're fixing it fast. But there's still some nets that are not using surround video. And I think ideally that all use surround video. Yeah. Mary. Yeah.
I think a lot of puzzle pieces are there for success. We just need more strong people to also just help us make it work.
Yeah, that is the actual bottleneck.
So that is the actual bottleneck, I would say, and really one of the reasons that we are putting on this event.
Exactly. Well said, Andre. That there's just a tremendous amount of work to do to make it work. So that's why we need talented people to join and solve the problem.
招人.
Thank you for the great presentation.
老马太聪明了。
Questions answered. But one thing is, when imagine that now you have a large amount of data, even unnecessary. How do you consider that, there is a forgetting problem in neural networks? Like, how are you considering those aspects? And also, another one, are you considering an online learning or continuous learning, so that maybe each driver can have their version of self-driving?
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning. We trained the system once, we fine-tuned a few times. That sort of goes into the car. We need something stable that we can evaluate extensively, and then we think that that's good, and that goes into cars. So we don't do too much learning on spot or continuous learning. And
这个机器人真的是太绝了。
But there will be settings that you can say, like, if you are you typically a conservative driver, or do you want to drive fast or slow? You know, it's like I'm late for the airport. Could you go faster than, you know, basically the kind of instructions you'd give to your Uber driver. It's like I'm late for the flight, please hurry, or take it easy, or you know, whatever your style is. So let's take a few more questions here, and then we'll call it a day.
All right. So as our models have become more and more capable, and I guess you're deploying these models into the real world, one thing I guess that's possible is for AI to become more, I guess, misaligned with what humans desire. So I guess, is that something that you guys are worried about as you guys deploy more and more robots, or do you guys like, we'll solve that problem when we get there?
Yeah, I think that we should be worried about AI. Now, like, what we're trying to do here is, say, narrow AI, pretty narrow, like just make the car drive better than a human. And then have the humanoid robot be able to do basic stuff. You know, so at the point at which you sort of start to get to superhuman intelligence, yeah, I don't know, all bets are off. But you know, and that's it's, you know, that'll probably happen. But what we're trying to do here at Tesla is make useful AI that people love and is unequivocally good. That's our, you know, we'll try to aim for that. Okay, maybe one more question.
最后一个问题了，马上结束
My
了。
question is about the camera sensor. In the beginning of the talk, you had mentioned about building a synthetic animal. And if you think about it, a camera is a very poor approximation of a human eye. And a human eye does a lot more than take a sequence of frames. Have you looked into, like, there are like, these days are like cameras like event cameras. Have you looked into them? Or are you looking into a more flexible camera design or building your own camera, for example?
Well, with Hardware 4, we will have a next generation camera. But I have to say that the current cameras, we have not reached the limit of the current cameras. And I'm confident we can achieve full self-driving with much higher safety than humans with the current cameras and current compute hardware. But you know, it would be good to be 1,000% better rather than 300% better. So we'll see continued evolution on all levels in pursuit of that goal. And I think in the future, people will look back and say, wow, I can't believe we had to drive these cars ourselves. You know, it'll like self-driving cars will just be just a normal, like self-driving elevators. You know, elevators used to have elevator operators, and there's someone there with like, you know,
妈妈又讲了自动驾驶将来有一天就跟
operating the elevator,
现在的
and
电
then
梯一
every now
样
and。then they'd get tired or
自动
you
的
know, make a mistake and shear somebody in half. So
之前都是有人来操控电梯，现在谁还敢相信人呢？
elevators automatic, and you just go and you press the button, and you can be in a 100-story skyscraper and don't really
这个
worry
比喻
about
他
it.
用
Just
了
go
好
and
几
press
次
the
了，我
button,
们视频也
and
讲过。
the elevator takes you where you want to go. But it used to be that all elevators were operated manually. It'll be the same thing like for cars. All cars will be automatic, and then and electric, obviously. So there will still be some gasoline cars and some manual cars, just like there are still some horses.
他说到时候街上还是会有汽油车，会有人开的车，就跟现在看到街上也有马是一样的。太牛了！大家看完之后觉得明天股价会如何？再聊会儿啊，400个人一下就散了。啊，已经完事儿了。还有人想聊天吗？哎呀，7个月前我居然能猜到，今天看到了，我真的是震惊了。4.0不提啊，本来他说3.0确实已经足够了，4.0估计可能再需要下一个阶段的自动驾驶吧。 我是觉得它这个机器人吧，还挺那个什么的，就是如果你想象这个发布会如果没有机器人的话，对吧？是不是就只讲一下超级计算机，然后我们前面700-800个人听了快2个小时，什么都听不懂，然后他突然结尾来了一个机器人，是不是气氛瞬间就引爆了？我自己都嗨了。然后其实这个机器人没有造出来，对吧？他是说了明年才可能有样机出来，今天那个是个假人在里面跳舞，但是他这个故事讲出去了，他直接把他招人的目的讲出去了。你现在加入特斯拉，明年你就可以跟着我们一起来造机器人。你造出了，你现在加入特斯拉，你还可以明年跟着我们一起来做机器人，对吧？所以对，超级计算机是现货，机器人是期货，说的一点错没有。如果你只讲超级计算机，肯定不会有这个机器人的这个爆点，你知道吗？老马是营销天才啊，老马太聪明了，真的。这个机器人它现在完全连样机都没有，对吧？但是他讲了身高体重，包括用什么芯片，怎么样的。哎，对，它主要这个目的，我要有一个引爆点，把人才吸引来。现在你想，我靠，现在世界上谁来做机器人？我要去特斯拉，我能做机器人，我还可以做这么酷的人工智能，我可以用世界上最强算力的Dojo计算机，这么多小的 module 堆起来，这么多的链，这么多的网，最后弄出一个这么个东西，然后算力是全世界排名前列，对吧？就一部分工程师可能不会是通过你这个 Dojo 来加入你，但是通过我靠，我有这么强的算力，我还可以将来一起造这么牛的机器人。真的就是从现货、期货、软件、硬件，从这个现在有的，将来给你画的饼，我说画饼，我觉得一点问题也没有啊。这个饼7个月前我都能想到，对吧？就这个事情，哎呀，怎么说呢？你要让它现在体现到股价里，那就有点那个叫什么，不太现实，也没有必要，对吧？因为这个包括 Dojo 也是，他说明年才可以来完成这个全部的 implementation， 然后在完成 implementation 之后，然后才可以去解决世界上的真实的问题。所以你要说这两个东西其实对明天、后天或者今年年底的股价影响，实质性影响可能没有很多，对吧？但是就像我之前的视频说了，做这个发布会肯定是和电池日一样，都是更长远的影响，对吧？这个影响可能现在你回去看1年前的电池日，你都没有发现有什么影响，但是它是润物细无声那种感觉。但是它这次的目的就达到了，它这次的目的就是为了招人，对吧？所以只要把人能招过来，股价什么跌了，我觉得都无所谓，因为人才都来了，这些事情还做不成吗？还怕他做不成吗？对吧？而且马斯克画的饼真的实现的多，失败的少，这个是毋庸置疑的。对，机器人是真人，他一开始跳的时候他是放慢动作，然后一点点，然后拉得特别近，我以为是真的嘛，后来一拉开，一看是真人，对吧？唉，总之我觉得这个发布会挺成功的，比那个 Model S Plaid 的发布会要好看得多，而要成功的多，从整体来说吧。因为你想过，这个不是一个产品发布会，它并不是来发布 Dojo 计算机的，它也不是来发布这个 Tesla Bots 的，它的目的就是为了招人。但是你有没有发现，他在做这个发布会的时候用的功夫，远远没有他在用这个招人上面用的功夫、精力和时间。那个 Model S 发布的时候，老马讲完几句话就走了， 是不是走了？我记得他是走了。这个他从头带到尾，对吧？这个我觉得他就是对人才，对这个公司的未来的重视程度，远远比来展示我们这个Model S 发布这样的东西更在乎的多得多。这就是我觉得这是一家从 CEO 对吧？大家看到还有周围那些工程师，就真的就是还是 focus 上这个公司的长远的角度来说来做这些事情的。respect， 敬佩敬佩。我今天直播了好长时间啊，直播了几个小时，3个多小时了。大家散了吧，散了吧。你们散少点人，我就关了。还有啥问题没有？如果讲讲未来有一个原因让我卖出特斯拉股票，会是因为什么原因？自己缺钱吧，可能又不得不卖，或者是 I don't know， 就特斯拉出了一些特别严重的问题吧。谢谢大家，谢谢大家，这么长时间一直听我在这儿胡说，然后吃饭。这个比电池是效果要好啊，我觉得。谢谢大家，谢谢大家。去特斯拉上班，有心无力啊。大家都歇了，散了，回去我看看这个视频怎么拍，头疼。谢谢大家，谢谢大家，好多人啊。老马被暗杀了，哎呦！散了吧，散了吧。估计有的人他不是第一时间，他就还看到一半儿，然后，所以感觉人还挺多。总体来说，今天还是很开心的，没去这个游艇还是挺值的。哦，他昨天暗示了是吧？谢谢大家，500人以下我就关了啊，再聊一会儿。谢谢大家，谢谢大家。 老马确实越来越胖了，我刚刚看的那小肚子太可爱了。哎呀，哪家公司的股东还担心这家公司 CEO 胖不胖？你不觉得特别好玩吗？谢了吧，各位，谢谢大家。我尽量整点视频出来吧，太干了，主要是太干了。我要纯讲技术吧，我又不是专家，说白了，我觉得我还是从这个影响方面讲吧，就讲一些数据，讲一些影响，讲一些长远的东西吧。因为这个太专业的东西，我也讲不明白，也误人子弟，对吧？就算我讲明白了，感觉就刚才那个东西，特斯拉的这个东西，换成中文讲，咱们也听不明白啊，我是这么觉得的。好了，关了，谢谢大家。